Zendeleev, we'll go with that. My name is Professor Zendeleev, and I am his cousin of the, of course, very famous Zendeleev, who invented the periodic table, which we will have a lot to talk about today. Now, anyway, I'm going to be teaching you a very important lesson called about bonding. So bonding. Yes, very good bonding.
Professor!
Yes, you!
What are the differences between element and compound bonds?
Oh, that's an excellent question. Well, first of all, there are three different types. There's metallic bonding, there's ionic bonding, and there's covalent bonding. Now, metallic bonding can only happen between metals. So, it is said to be only an element. Now, but with ionic, for example, it can only be compound, as it is the chemical attraction between metals and non-metals. And it's, of course, the positive and negative attraction of the ions together. But with covalent, very unique little covalent, covalent can either be element or compound. For example, it can be element such as oxygen, where it has two of the same kind of atom. But it can also be compound, as for example, water, with hydrogen and oxygen.
Professor?
Yes, you're back.
What's the difference between pure covalent and polar covalent bonding?
Ah, excellent question indeed. But first of all, there is pure covalent. Now, pure covalent is intramolecular, and it happens between atoms, but non-metal atoms of course, of the same element. So for example, there is oxygen, and with this oxygen, they share the electrons equally, and it's a very strong bond. And then there is polar covalent. Now, polar covalent happens with non-metal atoms of a different element, and it's all to do with electron negativity. So for example, with carbon and oxygen, because oxygen has a higher electron negativity than carbon, it then pulls more of the electrons towards it, which creates a polar bond, polar covalent bond. And this is, of course, intermolecular, and is also a very strong bond. Alright class, now I'm going to ask you now, what is the difference between the bonding and the properties? And let's look first of all at melting point and boiling point. Can anyone tell me?
Professor?
Yes, you at the back.
Ionic and metallic compounds have high melting points. That's why metallic bonds usually are solids, and ionic compounds are usually solids too at room temperature. Covalent networks have high melting points, so they are solid too. Covalent molecules have low melting points and boiling points, so they can be gas, liquid or solid at room temperature.
Ah, yes, absolutely, spot on. Dr. Ben. That's funny, yeah? Right, anyway, yeah, so that was absolutely correct. Things such as covalent networks have very high melting and boiling points. Because, for example, in graphite, there are lots and lots of carbons. Now, oh, stop laughing at the back! Now, all the carbons, they join together like this. And because they are all joined together, they have very, very high bonds, meaning the melting point and boiling point is extremely high. Now, that is melting point and boiling point. Can anyone tell me about electrical conductivity? Anyone?
Professor?
Yes, you back.
Metal compounds are the only ones that conduct when solid or liquid. Covalent molecules are non-conductors in all states, and covalent networks are non-conductors, apart from graphite is an exception. Ionic compounds are non-conductors when solid, and good conductors when molten or in aqueous solutions.
Yes, that's absolutely right. So things such as ionic compounds, they only conduct when they're molten, because the ions are then able to move, they're free to move. Now then, we move on to another thing. Can someone tell me about solubility with bonding? Anyone at all?
Professor?
Yes, you!
Metallic compounds are soluble in polar and non-polar solvents. Covalent network compounds are insoluble in all solvents. Covalent molecules are insoluble in polar solvents but soluble in non-polar solvents. Ionic compounds are soluble in polar solvents and insoluble in non-polar solvents.
That's absolutely right.
Professor?
Yes, you're the back.
Yes, what are the other types of bonding?
Oh, that's a very good question, yeah. There are other types of bonding, and these bondings are very weak compared to the other ones I explained earlier. One of these types of bonding is called van der Waals forces. And van der Waals forces is simply the force between electrons and protons that are racing around the atom. Let me explain. So, we have an atom, and then the electrons race around the atom as shown. Sometimes there are more electrons on one side of the atom than on the other, creating a negative and a positive charge on each side. This is known as a temporary dipole. Now, because of this means that the other atoms also have a temporary dipole, meaning that this side is positive and this side is negative. So, they attract, yeah? So this attraction is known as van der Waals forces and happen between atoms in all the time. But these are extremely weak. They are so weak. I can't even explain how weak they are. Now, there are other forces as well, such as polar. Now, as you can see here, as I've drawn before, very quickly, there are forces called polar. Now then, these are based upon electron negativity. So here I have two propanons. Now, because of electron negativity, the oxygen and the carbon attraction between the shared electrons is stronger than the oxygen. Therefore, it has a negative charge, and this carbon has a positive charge. This then happens again in the same propanon as here. So, with this in mind, these two then attract like so, creating what's known as a polar attraction. And the thing about these bonds is they are permanent bonds, and they happen between all these molecules like so. But again, they are very weak and not as strong as the other bonds. Now, there's another bond as well. This is simply known as hydrogen bonding. Now, hydrogen bonding can only happen between hydrogen and nitrogen, oxygen, and fluorine. Now, between these, this also happens to do with electronegativity. So, with water, for example, we have here the water molecule. Now, due to the fact that the oxygen has a higher electronegativity than hydrogen, it then has a bigger attraction for the shared electrons. Therefore, it has a negative charge, and the hydrogen has a slight positive charge. Now, again, we have another water molecule here, and this happens again with this being looks like a 6, with this being a negative charge, and this now being a positive charge. And so these then simply attract with each other. This only happens with hydrogen and with nitrogen, oxygen, and fluorine. It is the strongest out of the other two bonds, but it is still very weak intermolecular bond. Alright students, that is my lesson over about bonding. I hope you've all learned some stuff, and I'll see you all later. Ha ha ha. Oh, das ist sehr gut. Ja, das ist sehr gut. Good morning, class. My name is Dr. Zendeleev, and I shall be your science teacher for this morning. So as you can see, we have some very complicated stuff on the board, but that has absolutely nothing to do with what we're doing today.
Oh, no, where's Randall? Oh, he's up the top.
Thank you very much, yeah. Welcome.
You can read it.
Reading of a lecture. Of racing around an atom at really quickly speeds. My beard has fallen off. Right, class. Now, the next thing I want you to think about is what is the relationship between bonding and alright, that's it. Alright, class. Now,
Professor?
Yes, what's that?
What is the difference between pure covalent and polar covalent bonds? Professor?
Yes, what's that?
What's the difference between polar covalent and pure covalent bonding?
That's a brilliant question, yeah. Well, pure covalent and polar covalent is simply the difference. Well, there's, okay, wait, let's get that one up.